Look up. That star, bright and fierce, is a ticking clock, but not just for itself. It is the visible sign of a subtle, terrifying process already underway, a process dictated by an invisible, relentless executioner: dark energy. The true beginning of the end did not happen in the distant future. It began billions of years ago, when the expansion of the cosmos shifted gears, transitioning from deceleration, caused by the gravitational pull of matter, to an accelerating rush into oblivion. We are living in a moment of cosmic euphoria, a fleeting epoch where the energy density of the vacuum itself is winning the ultimate battle against gravity. This is not just theoretical decay, we can observe it. Distant galaxies are not merely moving away from us, they are accelerating away. And the most chilling consequence of this acceleration is not merely loneliness, it is censorship. As time progresses, the accelerating expansion will push galaxies outside our observable horizon. Eventually, the light from these distant island universes will be stretched so thin, redshifted so violently, that it will become invisible, effectively erasing them from existence. Trillions of years from now, our closest galactic neighbor, Andromeda, will have long since merged with the Milky Way to form Milkomeda. But that colossal supergalaxy will be an island, a solitary speck in a sea of ever-expanding, empty blackness. There will be no cosmic web visible, no background of other galaxies to measure our velocity against, no evidence that the universe was ever anything more than our isolated, dying cluster. The fundamental ability to perform cosmology, to study the structure and history of the universe beyond our immediate grasp, will vanish. Future civilizations, if they exist in that lonely era, will be confined to their local cluster, falsely believing they live in an empty, static universe. They will be starved of the data that proved the Big Bang, starved of the evidence of the trillions of other homes that once existed. The first major casualty of the universe's demise, therefore, is knowledge itself. This relentless acceleration, driven by the mysterious negative pressure of dark energy, sets the stage for the longest, coldest, and quietest death imaginable. It guarantees that the ultimate end will not be a spectacular explosion, but a protracted, silent freeze, the Big Freeze, or heat death. This realization that the forces of expansion are systematically destroying the very history and structure of the cosmos should chill you far more than the idea of a single supernova, because that supernova, however violent, is still a sign of life, a brief flicker of creation. The expanding void is the absolute cessation of possibility, the final, cold mechanism of universal decay that no physics can reverse. This slow, deliberate erasure of the cosmic canvas is the fundamental horror underlying all future predictions, defining an epoch where existence itself becomes fundamentally sterile and unsustainable. It is the invisible current pulling the entire structure of reality towards zero temperature and maximum entropy, long before the stars truly die. The glorious epoch we inhabit, the stelliferous era, the age of stars, is merely a short, vibrant youth in the cosmological timeline. It is destined to end, not with a bang, but with the slow, irreversible exhaustion of fuel. We have already lived through about 13.8 billion years of stellar creation, but the future timeline stretches out for trillions of years before the cosmic lights finally dim. The first step in this long decay is the simple cessation of starbirth. Currently, giant molecular clouds are abundant, providing the raw material, hydrogen and helium, needed for gravitational collapse and ignition. However, the relentless expansion is stretching space, making these clouds thinner and more dispersed. Over the next 10 trillion years, star formation will gradually halt. New stars will become impossibly rare events, and eventually, the last true star will form, burn its fuel, and fade. When that final star goes dark, the universe will enter the degenerate era, an age dominated entirely by stellar corpses. The most massive stars have already collapsed into neutron stars or black holes, but the vast majority of stars, the Sun included, will eventually shed their outer layers, creating beautiful planetary nebulae and leaving behind white dwarfs, intensely hot, incredibly dense remnants about the size of Earth, cooling slowly over unfathomably long timescales. The lowest mass stars, the red dwarfs, are the longest lived, burning their hydrogen fuel so efficiently and slowly that their lifespans can stretch for 10 to 100 trillion years. They are the final candles in the cosmic cathedral. As the hydrogen is consumed, these little embers will slowly transition from burning red bright to cooler blue dwarfs and then finally fade into cold, dark lumps of matter, the black dwarfs. A black dwarf is essentially a frozen carbon ember, still possessing mass but emitting no light or heat. They represent the perfect cosmic tombstone. The problem, however, is that even these stellar remnants are not eternally stable. Over the immense periods of time involved, gravitational encounters between these stellar remnants within the merged Milky galaxy will gradually eject some of them entirely into intergalactic space, condemning them to absolute isolation in the accelerating void. Others will fall toward the massive black holes at the galactic center. The structure of the galaxy itself begins to dissolve, governed by the brutal efficiency of Newtonian gravity over timescales vastly exceeding the age of the universe. This era transforms the vibrant, light-filled universe we know into a sparsely populated graveyard, where light is a memory and the only remaining heat emanates from the faint, dying glow of contracting white dwarfs or the slow rotational friction of neutron stars. This vast, dark expanse is punctuated only by the occasional collision between two black dwarfs, perhaps sparking a brief, temporary, and utterly futile supernova of sorts, a momentary flash of heat and light that quickly succumbs to the crushing cold. This is the prelude to true universal silence, the era where the forces that create life and structure are finally vanquished by the cold arithmetic of thermodynamics and time. Once the stars have faded and the stellar remnants have cooled, the universe enters a phase so foreign to our current understanding of stable reality that it borders on science fiction, the era of disintegration. The fundamental building blocks of matter itself, the protons and neutrons that make up every atom in your body, every planet, and every white dwarf, may not be eternal. According to many modern grand unified theories, guts, which attempt to combine the strong, weak, and electromagnetic forces, the proton is unstable. While laboratory experiments have not yet detected proton decay, the minimum predicted half-life is astronomically large, somewhere around 10 to the 34th to 10 to the 37th years. If proton decay is real, then everything, the core of the black dwarf, the crust of the neutron star, the quantum structure of reality, will slowly, agonizingly dissolve. Imagine the timescale. 10 to the 37th years is 100,000 trillion years. Even if the probability of a proton decaying is minuscule in any given second, over this cosmic immensity, statistical certainty takes over. Every single proton in the universe is guaranteed to decay, transforming into lighter particles like positrons, neutral pions, and highly energetic gamma rays. This process is the ultimate dismantling of structure. The black dwarfs, which had been cooling slowly, suddenly become unstable. Their solid, crystalline carbon cores would begin to evaporate from within, atom by atom, dissolving into clouds of high-energy radiation and elementary particles. Chemistry ceases to exist. There is no longer any stable matter capable of forming structure, supporting life, or resisting gravitational collapse. The universe is rapidly reduced to a diffuse, low-density gas of electrons, positrons, neutrinos, and photons, expanding ever faster due to the dark energy background. Even the most bizarre stellar remnants, the neutron stars, face dissolution. While initially thought to be immune due to their extreme density and the influence of the strong nuclear force, if protons decay, the neutrons within the star, which are often considered to be protons and electrons compressed together in this context, will eventually follow suit, turning the ultra-dense matter into a burst of energy and light particles. This widespread atomic decay is the universe's final structural collapse, a transition from complexity and matter to simplicity and pure energy. The surviving electrons and positrons, moving incredibly slowly in the nearly absolute zero background temperature, might occasionally interact and annihilate each other, generating even more photons, but these events will become increasingly rare as the particles drift further apart. The entire cosmic density, already incredibly low, approaches zero, leaving behind a truly homogeneous, unstructured plasma. The great structures of the stelliferous era, the galaxies, the stars, the planets, are utterly gone, replaced by a thin, ghostly soup of fundamental particles clinging briefly to existence before their own quantum uncertainties overcome them. This phase, known as the degenerate era's terminal stage, ensures that the universe is scrubbed clean of all recognizable physical forms, paving the way for the reign of the cosmos's most durable, yet ultimately doomed entities, black holes. As the hydrogen fuel vanishes and protons decay, the colossal black holes, survivors of the intense gravitational collapses of the early universe and the mergers of thousands of galaxies, become the dominant features of the cosmos. By 10 to the 40 years, the universe is mostly composed of black dwarfs, neutron stars, and the towering supermassive black holes, or SMBHs, nestled at the centers of what were once galaxies.
But now, even the gravitational ballet ceases. Gravitational radiation, the ripples in spacetime predicted by Einstein, slowly saps the orbital energy of any lingering binary systems. Over unimaginably vast timescales, every orbiting pair, whether it's two black dwarfs or two neutron stars, will spiral inward and merge. These mergers release bursts of gravitational waves, momentary echoes of energy in the vast, cold void. But the ultimate fate of all matter that managed to escape proton decay is to fall into a black hole. These black holes, growing over trillions of years by consuming the decayed remnants of the cosmos, swell to monstrous proportions, dwarfing the size of any star ever conceived. They will eventually merge into colossal, ultra-supermassive black holes. Imagine a black hole with the mass of 100 trillion suns, dominating a patch of space where a galaxy once flourished. This is the black hole era, stretching from roughly 10 to the 40 years to an astonishing 10 to the 100 years. In this age, the universe is defined by the slow, inexorable maximization of mass density within these cosmic singularities. Yet, even these ultimate gravitational prisons are not eternal. The stability of a black hole, once considered absolute, was undermined by Stephen Hawking's revolutionary work on quantum mechanics and general relativity. Black holes radiate. They are not perfectly black. They emit a faint thermal glow known as Hawking radiation. This radiation arises from the quantum vacuum fluctuations near the event horizon, stealing energy from the black hole itself, causing it to slowly, agonizingly shrink. The rate of evaporation is inversely proportional to the black hole's mass, meaning the smaller the hole, the faster it dies. A stellar mass black hole might take 10 to the 67 years to evaporate completely. A supermassive black hole, one of those final 100 trillion solar mass behemoths, might endure for 10 to the 100 years, a duration so vast that it dwarfs the age of the universe by a factor of 10 to the 89. This age, spanning dozens of orders of magnitude in time, is the true test of cosmic patience. During this era, the darkness is nearly absolute. The faint, expanding photons of the cosmic microwave background have been stretched into wavelengths longer than the observable universe itself, rendering the background temperature effectively absolute zero. The only warmth, the only light, the only source of energy anywhere in existence comes from the incredibly weak flickering emission of Hawking radiation.
These black holes are the final energy sources, generating a sparse trickle of particles until they explode in a final brilliant flash, an immense burst of light marking the complete erasure of their mass and the final loss of the ultimate gravitational structure. This is the beginning of the vacuum's absolute dominion. The evaporation of the last ultra-supermassive black hole around 10 to the 100 years into the future marks the true beginning of the final act, the Dark Era. This monumental evaporation concludes the cycle of destruction driven by gravity and the decay of matter. Everything that could be structured, everything that could burn, and everything that could collapse has finished its task. The universe has been reduced to an unimaginably dilute gas of photons, neutrinos, electrons, and positrons, separated by distances so vast that interaction is statistically impossible. The volume of space is accelerating its expansion so rapidly, driven by dark energy, that even particles that were once neighbors are rushing away from each other at rates far exceeding the speeds we consider normal. The temperature of the universe is now critically close to absolute zero, defined only by the residual heat of the evaporating black holes and the increasingly redshifted cosmic background radiation, which is now measured in fractions of Kelvin, approaching zero. In this era, the concepts of time and space, as we understand them, begin to lose meaning. Structure requires interaction, and interaction requires proximity, which the relentless expansion denies. The remaining elementary particles drift randomly, occasionally traversing the vast emptiness. An electron might travel for billions of light years before potentially encountering a single positron, resulting in a momentary annihilation event that produces a weak photon, immediately stretching and vanishing into the void. These are the only events remaining in the entire cosmos. Imagine the profound cosmic loneliness. We currently live in a universe rich with systems, interactions, complexity, and consciousness, a brief but glorious interlude of non-equilibrium physics. The universe is currently hot and organized enough to allow for the spontaneous combustion of creation, leading to stars, planets, biological life, and thought. But the Dark Era is the state of maximum entropy. Entropy, the measure of disorder, has reached its peak. All possible energy gradients have been flattened. All potential for work has been exhausted. There are no temperature differences, no pressure differences, and crucially, no stable pockets of organization. This raises the most profound question about our own existence. If consciousness is fundamentally an emergent property, a highly complex state of low-entropy organization that processes energy, then does the death of the universe represent only the loss of structure, or does it represent the absolute loss of meaning? If the entire cosmic history, from the Big Bang to the final flash of the last black hole, served only to create pockets of temporary awareness that are destined to be erased by the iron rule of thermodynamics, what inherent value did the fleeting consciousness we share truly possess in the face of universal, eternal silence? What does the unstoppable march towards heat death imply about the significance of our brief, brilliant existence? Does the knowledge of the universe's inevitable demise diminish the beauty of the present moment, or does it heighten its value? We are a glorious accident of non-equilibrium. Share your thoughts below on the existential dread or comfort this cosmic forecast brings you. This final vacuum, devoid of matter and energy gradients, is a state of permanent statistical stasis, where the only movement is the relentless expansion that guarantees ultimate cold separation. Having established the heat death, the cold, quiet end ruled by entropy, we must briefly consider the dramatic alternatives proposed by theoretical physics, scenarios that offer a quick, catastrophic ending rather than a protracted, cold decay. The two primary competing theories to the Big Freeze are the Big Crunch and the Big Rip. The Big Crunch is perhaps the most poetically appealing end, a reversal of the Big Bang. If the energy density of the universe, particularly the mysterious dark energy, were to somehow reverse its influence, or if the overall density of matter proved to be higher than currently measured, gravity would eventually overcome expansion. The expansion would slow, halt, and then reverse. Galaxies would begin rushing back toward one another, the cosmic microwave background would heat up, and space itself would contract. Stars and galaxies would merge violently in a fiery spectacle until all matter was compressed back into an ultra-hot, ultra-dense singularity, similar to the state before the Big Bang. This scenario suggests a cyclical, oscillating universe, a potential big bounce leading to a new creation. However, current astronomical data, particularly observations of Type 1a supernovae, which confirm the acceleration of expansion, strongly disfavor the Big Crunch.
The influence of dark energy appears to be stable and dominating. Then there is the Big Rip, the most violent and immediate possible end. This scenario relies on a hypothetical form of dark energy known as phantom energy, which possesses an equation of state more extreme than the cosmological constant. If phantom energy dominates, its repulsive gravitational effect wouldn't just accelerate expansion, it would increase in intensity over time. Initially, galaxies would be ripped apart, then individual stars and solar systems, then planets. In the final seconds before the singularity, the phantom energy would become so strong that it would overcome all fundamental forces, ripping apart atoms, tearing protons from neutrons, and ultimately tearing apart the fundamental fabric of space-time itself. The final singularity wouldn't be a compression point, but a moment when the scale factor of the universe becomes infinite, tearing reality into shreds. This is a dramatic end, but again, current measurements of dark energy suggest it behaves more like a cosmological constant, favoring the Big Freeze. The cosmological constant implies a constant energy density, while phantom energy requires an increasing energy density. The cold truth remains that the Big Freeze is the most probable fate. It is the end that requires the fewest exotic, unproven particles and adheres most closely to the observed rate of cosmic expansion. The universe is not destined to fiery collapse or instantaneous atomic annihilation, but for the slow, crushing indifference of increasing distance and cooling temperatures. It is a death by entropy, a gradual slide into ultimate disorder, where all information is randomized and every particle is too far from its neighbor to matter.
The immense timeline of the Dark Era, stretching beyond 10 to the 100 years, forces us to confront timescales that defy human comprehension. We enter the realm of quantum mechanics operating on cosmological scales, where the laws of physics become utterly probabilistic. This is the age of the final lonely particles, the electron, the positron, and the ubiquitous photon. These are the only things left that possess mass or energy. They exist in an ever-expanding volume, making the likelihood of any interaction vanishingly small. The distance between an electron and its closest neighbor could be larger than the size of today's observable universe. The vacuum of space, once seen as empty, is now the ultimate defining feature of existence, saturated only by the incredibly weak residual field of gravity and the ghostly omnipresence of dark energy.
In this profound cold, the particles move incredibly slowly. Their kinetic energy is negligible, driven only by the faint thermal energy remaining, which is approaching 10 to the minus 30th Kelvin. Even at this scale, however, the structure of space is still governed by quantum uncertainty. The Heisenberg uncertainty principle dictates that total stillness is impossible. Energy and momentum must fluctuate, leading to the bizarre phenomenon of quantum tunneling. Theoretically, over vast periods, even the largest structures still in existence, perhaps the occasional cluster of electrons bound by weak electromagnetic forces, will eventually tunnel away from each other. Every single event, every slight change in state becomes dictated purely by probability. Imagine a cloud of electrons drifting for a trillion years, and suddenly, due to a massive quantum fluctuation, they briefly group together into a structure resembling an atom, only to immediately dissolve back into the sea of expansion. These are temporary, fleeting echoes of organization. Perhaps the strangest prediction of this deep time involves the creation of Boltzmann brains. If the universe exists long enough in a state of maximum entropy, it is statistically inevitable that random quantum fluctuations will occasionally cause energy and matter to briefly assemble into complex yet temporary configurations. A Boltzmann brain is a fluctuation complex enough to possess momentary self-awareness, an isolated consciousness that flickers into existence for a fraction of a second, experiencing the terror of ultimate cold before immediately dissolving back into quantum fuzz. These concepts highlight the bizarre statistical necessity of structure in deep time, yet also its ultimate futility. The Dark Era is a testament to the fact that even in death, the universe cannot achieve perfect stasis. There must always be a faint, probabilistic flicker of movement, a statistical echo of the grand creation that once was. But these flickers are not the basis for a new cycle. They are merely the dying gasps of a system approaching true thermal equilibrium, where the distinction between organized matter and empty vacuum has been completely erased. Even as the Big Freeze establishes itself as the default trajectory, the cold, drawn-out death by entropy, there exists a mechanism of catastrophic destruction even more dramatic and terrifying than the Big Rip, the vacuum metastability event, or false vacuum collapse. This scenario doesn't rely on exotic phantom energy, but on a dangerous instability inherent in the very structure of the universe as we perceive it. Our current understanding of fundamental physics, particularly the Higgs field, suggests that the vacuum energy level we experience, the energy baseline that defines all reality, might not be the true lowest possible energy state. We might be living in a false vacuum, a metastable state perched precariously on a hill rather than resting securely at the bottom of the deepest valley of the universe's potential energy landscape. If this is true, the current vacuum is temporary and unstable. Over vast timescales, or perhaps triggered by an extreme energy event far beyond our cosmological horizon, quantum tunneling could cause a small region of space to spontaneously transition to the true vacuum, a state of lower energy. When this transition occurs, a bubble of true vacuum would spontaneously nucleate and begin expanding outwards at the speed of light. Everything inside that expanding bubble would instantly change. The fundamental constants of nature, the speed of light, the mass of the electron, the strength of the strong nuclear force, even the dimensions of space and time would be instantly reset to the new, true vacuum values. This collapse would not be a slow, cold fade. It would be instant, total, and irreversible. As the bubble of the new physics expands, it would completely rewrite reality in its wake, eliminating every structure, particle, and memory that existed under the previous physical laws. This possibility looms over the entire cosmic timescale, a statistical sword of Damocles. It requires no stars to die, no protons to decay. It simply requires the current physical laws to be slightly less robust than we assume. While calculations using observed Higgs boson mass data suggest our vacuum is relatively stable, the uncertainty remains a terrifying existential threat. It means that the fate of the universe might not be in the hands of the slow, cold laws of thermodynamics, but in the rapid, unforgiving statistics of quantum mechanics. Ending our cosmic story not with a sigh of cold air, but with an immediate, blinding flash of total non-existence. As we hurtle past the 10 to the 1,000 year mark and beyond, the universe has entered a realm of ultimate probability and statistical madness, often termed the era of black eternity. This phase is fundamentally different from the dark era that preceded it because virtually all mass and all coherent energy have vanished. The only remaining entity with any kind of physical presence is the electron, the smallest stable charged particle. The universe is now a ghostly sea of ultra-diffuse electrons and positrons moving so slowly, so far apart that the gravitational influence between them is entirely negligible. Their potential energy from electromagnetic forces is also minimal due to the immense distances separating them. Time dilation effects become bizarrely important in this era. For an individual electron, the concept of time barely has meaning. The only interaction it might experience in 10 to the 300 years is a momentary fleeting attraction to a similarly charged particle, quickly overwhelmed by the general expansion. Eventually, even the electron itself faces an uncertain fate. If the electron is stable, as currently believed, it remains as the longest-lived particle. However, theories involving gravity and quantum tunneling suggest that even electrons might eventually decay into photons, though the required timescale exceeds 10 to the 2,000 years. In this final, coldest state, the universe has achieved perfect thermodynamic equilibrium. It is homogeneous, uniform, and featureless, except for those fleeting quantum fluctuations. The total energy density of the remaining particles approaches zero, leaving the persistent background density of dark energy as the solitary force dictating the geometry of space-time. The universe becomes literally featureless, a blank slate where the concept of location or structure is meaningless. The vast, empty space is still expanding, pulling the last remaining particles further and further apart, ensuring that the last cold separation is absolute. This is the ultimate victory of entropy. Nothing can be organized, nothing can interact, and nothing can generate heat or light beyond random statistical quantum noise. The silence is perfect, the cold is absolute, and the energy potential is zero.
This is the definition of cosmic death, the end of potentiality, the universe having fully spent its energy inheritance from the Big Bang, sinking into an endless, cold repose where even the fundamental particles are on the verge of fading into non-existence, their electrical charge the final faint memory of the energetic epoch that birthed them.
The journey through deep time culminates in a profound philosophical realization. The Big Bang was a moment of supreme violence, density, and heat, yet the ultimate destiny is one of total passive silence and infinite cold. The universe, born in a furnace, dies in a refrigerator. The contrast is astonishing, a rapid onset of creation followed by an eternity of decay. Our entire human story, the history of Earth, the evolution of stars and galaxies, is contained within the first few trillion years, a tiny, almost instantaneous flicker of light and warmth against the backdrop of billions of years of silent dissolution. We exist in the high-energy residue of the initial expansion, utilizing the temporary non-equilibrium state created by gravity and stellar fusion. Our significance, perhaps, lies not in enduring the ultimate cold, which is an impossible task, but in being witnesses to the beginning of the story. The final cold, infinite void is a terrifying prospect because it negates all effort. Every action, every thought, every structure built by sentient life is ultimately meaningless to the physical laws that dictate the end. Yet this very finality also defines the beauty of the present. Our brief conscious moment in the stelliferous era is a defiant act against the entropy that is destined to win. We are the universe observing itself, creating complex information and beauty in a temporary fight against the dispersal of energy. In the final cold, when electrons are too far apart to even feel the faintest tug of attraction, when the last photon has redshifted into oblivion, and the temperature is defined only by the zero-point energy of the vacuum, the universe will enter a state of true, eternal thermodynamic equilibrium. There is nothing left to happen, no further change is possible. This silent, eternal end forces us to value the complexity and warmth of the now. We are the brief, brilliant resistance against the long night, and that resistance, however temporary, is the only true meaning we can assign to our cosmic existence. The true horror isn't the explosion or the instantaneous destruction, but the endless empty time after the destruction is complete, where nothing, not even possibility, remains. We are privileged to inhabit the warm edge of creation, standing against the backdrop of the coming cold, and perhaps that privilege is everything.